Hello everybody. In this exercise we are going to study the grid code compliance of wind farms. For this purpose we are using a system which consists of 10 wind turbines that is connected to AC grid via AC transmission. If we open the provided Simulink model for this exercise, we can see that it also consists of 10 wind turbines which are connected to each other by the AC cables between the wind turbines, and then there is a offshore compensation and transformer, also export cable, onshore compensation and transformer, and finally we have the AC grid. The wind turbine model in this exercise is similar to the one we developed in the previous module. Actually, the one that we developed in previous module is a simplified version of this wind turbine model. You can open the dialog box of the wind turbines and see what are the parameters used here. You can change the name of wind turbine also using this dialog box. For the simplicity, we only measure the signals of one wind turbine, and we assume that all of them operate in a similar way. If you want to know where this measured signal is sent to, we can open the go to block and click on it. Then it brings us to the received block. If we go outside and also press space bar to fit the model to the window, we can see the reference and measurement block is also highlighted because the received block is inside. The other component that we are using here is this AC cable. We can see that it is modeled as a equivalent pi model of the cable. Also, we have this shunt compensator, which is simply a branch or inductor with a given value. We have export cable with the parameters and also the lengths of the cable. And we have also onshore compensation transformer, and finally the grid with the internal impedance that we see here. Another block in this model is this wind power plant controller. If you open the dialog box, you can see there are control modes. At the moment, they are set to the fit-through control mode, which means the input is directly going to the output. And if you go inside the model, we can see that the controllers are deactivated and the inputs are directly connected to are sent to the output, and the controller is bypassed. We can change the control mode here to see the impact inside of the model, and you can see that now the P and Q controller were activated. Let's bring them back to the fit-through control mode. And another block in this model is this reference and measurement. We already saw that wind turbine signal is sent here for plotting purposes. We can find the reference of or the source of our signals by again double clicking and following the links. If the signals is sent from the same window, you can simply select the from block and see that the associated go to plug is highlighted. Otherwise, we simply just open the from block and use the link to understand where it is coming from. Also, let's look at the model settings. Here we can see that the start time and stop time. Also, we can change the stop time on the main tab of the Simulink model. The solver is also discrete, so it looks fine. And also in the model properties, we can go to the callback and see that the model is initialized with the parameters. But the problem is that we have these warnings on the command window. This happens because the variables are not detected on the Simulink model when we open them. So let's try to close our Simulink model and make sure that the variables are available on the workspace before opening the Simulink model. We can do that by opening this parameter file and then run it. You can see you can look into the parameters and see which values are defined here. Now the values are available in the workspace. If we open the Simulink model, we can see the value of the variables are detected here in the Simulink model, and you can check it for each component. Also, if we go to the command window, we can see there is no warnings, and that is because the variables are available in workspace. To make it automatic and make sure that the parameters are available always when we load the model, we can go to the callbacks and this preload function and run the parameter file from here. So now if we save it, we and close it, we are sure that the parameter file is run before loading the Simulink model. So let's clean up the workspace by clearing all the variables at the workspace. Now if we open our Simulink model, we can see that there will be no warnings. Now the command window was cleaned up because there is this clear command window in the script that after opening the Simulink model, we can see the parameter values will be detected on the model as well. For example, for cables, we can see the values also for wind turbines. And on top of that, there will be no warning in the command window because the values are available in the workspace. So in this way, we can avoid those warnings. There are some information about the model and also the task that we will be doing here. About the reference values, and it mentions that it is built in 2018B because the first time that I created this model it was 2019, but this version is saved in 2020B. You can also see this information in the model properties in the main window. You can see the last saved and also created on. Also in the info, you can see who has created the model and who has saved it last time and on which dates. These are some information that you can find on every Simulink model if you like. Yeah, the rest are some information about that, what we are going to do is about the checking the compliance of wind power plants with the grid code requirements. And we saw that the offshore wind power plant is set to the fit-through control mode. Also, we don't need to be worried about these parameters because we added it to the initial function of the Simulink model. In the first task of this exercise, we are going to run the Simulink model and see if it is complying with the grid code requirements. So let's run the Simulink model. To save time, I have speeded up the simulation. Actually, the video 10 times. So this is 10 times faster than what it is really. So if it is slower than this on your computer, it's normal because now the video is running 10 times faster. Now it is done. We can we can go to the reference and Simulink and the measurement signals and look at the signals. For example, the reference value of wind power plant. This is the exactly same as the reference of wind turbines because the control mode is fit through. And here we are trying to cover the limits of wind turbines for active and reactive power. So it goes from 0 to 100% for active power. Then when the active power is constant, we change reactive power to cover the limits of the reactive power for the wind turbines. We can also see the value of the P and Q for wind turbine and also the measured value of the wind power plants. It's a bit different because of the cables in between. if you want to know where this P and Q are measured exactly, we can follow the signals. So this is measured at this bus, at this measurement bus. Also similar for the other P and Q, which is onshore measurement. So we follow the signals and we can see that it is measured onshore. The previous one was offshore, which is called as a wind power plant P and Q. The other point that is important to know is in the scope settings, we are logging the data to workspace to use them for the plotting purposes. So you can see the names and the saving format of the signals in each scope. You can open all the scopes and go to logging to see the variable names. Also, you can find them in the workspace. These are the values which are logged to the workspace from Simulink model because we run the Simulink model, so they are available here. If you open them, we can see they consist of two columns. One is time, another is value. Based on this, we can open now the plot function. Here it is the second column of the signals is used, which is the values of the signals. So in this plot, we are going to plot the Q against active or against P for wind farm and wind turbines, and see if it is available. If we consider also the sampling time or time step in the simulation, we can understand that this 10,000 to 31,000 is equivalent to first second to 31st second of the simulation. We can check it also by looking at the measurement signals. So if we go to the 10,000 row, we can see it is first second, and the final one is the 31st second. So we are plotting the P and Q from first to 31 second. The other point is that make sure that there is no clear all. For example, to clear all the values from workspace, because we are going to use the available values in the workspace for plotting purposes in this MATLAB script. Now let's run the script to get the PQ charts. Here we can see the PQ chart for the wind turbine references and the measurement of the wind turbine. These two, the PQ charts are overlapping because wind turbine is following the set points and is generating the required PQ chart based on the reference given to it. The other one is in this black is the PQ chart measured at the offshore point of connection, which is wind power plant PQ. And finally, we have the PQ at the onshore point of connection. The last one is also the requirement for onshore connection. So before everything, we need to understand what does this onshore PQ requirement means. It means that the system should be able to provide the PQ for every point inside this chart. So it means that the onshore PQ chart of the wind farm, which is the shifted a bit to right in this case, should be able to cover all the points inside this requirement chart, but it is not covering this left part of the requirements. So it means that we need to add a compensator to cover this part of the requirement as well. So here we can say that no, it's not covering, as we discussed earlier, and we need to add a reactive compensator to compensate for this. To understand why we need a reactive compensator, one simple solution is that the cable is dominated by its capacitor, and for compensating it, we need to add a reactor to compensate for the capacitive behavior of the cable. The other one is that this PQ chart as onshore point of connection is shifted to the right on the reactive power axis. So it means that if we want to shift it to the left to cover the requirement chart, we need an inductor, or we need to consume a bit of reactive power. Based on this understanding, we can design the compensator. But before that, let's discuss a bit about the graphs. At no load condition, or when the P is very small, the impact is mainly coming from the capacitance, because the voltage is already there regardless of the flowing current. So for example, between the wind turbine and offshore point of connection, there is a small cables of the collector system, and that is why the PQ chart at offshore is shifted a little bit to the right respect to that of the wind turbine. When we increase the active power, it means we are increasing the flowing current in the system. The voltage is not affected much, so the reactive power generated by the capacitors will not be affected, but the reactive power consumed in the reactors, which are in series with the in the system, will be increased when the current is increasing. Also, if we consider a PQ chart at onshore point of connection, we can see that it is shifted to the right because of the long export cable, which introduce a high amount of capacitance between these 2 points. And also the uh, deviation, or the curve shape of this graph is more bold respect to the offshore one, because of the long export cable, and also two transformer which introduce a higher inductance between these 2 points. Note that this onshore PQ chart is achieved by setting the reference of the wind turbine to the limit of the wind turbine capacity. So it means we can reach to all the points inside this graph, but nothing outside of the graph can be achieved by changing the set points of the wind turbine. That is why we are going to add a compensator. Now let's compute the inductor for compensating 32 megawatts using the voltage at the onshore point of connection. So we can compute that and insert the value into the onshore compensation. Yeah, or maybe the value was 81. Yeah. Now if we run the model and again make it 10 times faster, the video. So the model is running without any error. After running, you can look at into the reference and measurement block and watch the scopes. But let's run the plotting script to get the PQ charts for. In this case, here we can see that the PQ chart at onshore point is shifted toward left because of the presence of onshore compensation. Also, another point is that in this case, the impact of the inductor of the export cable is clear because the deviation of onshore point of connection is larger than the offshore one. The PQ chart is covering almost fully the PQ chart requirements at onshore point of connection. There are small deviations, the small parts which are not covered, but this can be coordinated between the stakeholder and the system operators with a good intention. You can always look into the model and interpret the result. For example, at no load, all of them are overlapping, all the PQ charts are overlapping. But when the load is increasing, there are some reactive power consumptions in the inductor of the cables, and we see this deviation when when the active power is increased. In the next section of the exercise, we are asked to make 0 the reference of the reactive power, comment out the offshore compensation, and run the model. So let's see what is called the voltage at offshore point and find it here. So it should be this one. Yes, if you look at the this measured voltage, we can see the impact or the behavior of voltage at the offshore point of connection. So the voltage in this case is inside the 1.1 or is under 1.1 that is mentioned in the exercise. Yes, but there is a huge deviation in the voltage. Also we can run this PQ chart again. In this case, this is only a line of the PQ chart that we saw there because the reactive power is 0. The reactive power is 0, and only active power goes to the nominal and comes back to 0. So we can see the trajectory of this line from wind turbine reference uh, to the PQ of onshore and offshore point of connections. You can think about how would it look like these lines if there was no if the onshore compensation was also if the offshore compensation that we commented out was there, or what if there is no compensation at all. So for example, these things are the things that you can will help you to understand better this chart by comparing the trajectory lines that we got in this plot with the ones that with the PQ charts that we got in the previous part of the exercise. Now in this one we are going to change the control mode of the wind power plant to voltage control and see the impact on the system. So here we have the reference value over voltage. It is a step, but if we open it, we can see that the final value is also 1, so there is no step actually. Then let's change the control mode for reactive power to voltage. Now this wind power plant controller will control the voltage, and you can see that the QU controller inside this wind power plant controller is activated, and the controller is basically a PI controller for removing the error between the reference and measured signal, which is voltage in this case because we chose the control mode as voltage controller. After running the model, yeah, this is again 10 times faster. My PC is not that fast. uh, we can go inside this measurement block and see the voltage now. If we open this voltage is the measured voltage at offshore point of connection. Look at the values on the left side on the y axis. The voltage in this case is really close to 1, and it is done by sending the appropriate references to the wind turbines for generating reactive power. You can look at the PQ chart. It doesn't give any meaning except that you can see, for example, the mapping of PQ of the wind turbine on the PQ of the onshore point of connection and offshore point of connection. If you like to have an understanding of these facts. In this case, we have set the wind power plant controller to the voltage control mode. To understand how it is working, we can follow the signals. So the inputs are the voltage to this one. The measured voltage is the measured voltage at offshore point of connection. So you could see basically that the output of the wind power plant, which is connected to the input of the wind turbines, is based on the measured voltage at the offshore point of connection. So that's how the reactive power of the wind turbine is generated. So it is generated such that the voltage at on offshore point of connection is kept at 1 or very close to 1. In the next part, we are asked to introduce a step in the voltage, in the reference voltage, then observe voltage and reactive power response of the wind turbine. Also, we are asked to obtain rise time and response time of the voltage controller. So let's do that and introduce a step in the reference of the voltage. We have chosen 15 as the step time because at this moment the reactive power is constant and it's not changing. So we are sure that the system is operating at a steady state, and the transient that we will observe in the voltage or other signals is coming from this step in the voltage. Now we can, after running the model, we can open the voltage and add a cursor measurement to obtain the rise time and response time of the voltage. Let's make the first cursor to 15 because we know that the step in the voltage is started here. For the rise time definition varies a bit depending on the system. Here, let's say that the rise time is the time it takes that the signal reaches to the 90% of the step value. The step value is 5% here, so we can obtain the rise time by setting to the second cursor to the time at which delta y is 4.5%, which is 90% of 5% that we introduce in the voltage. Also, for the response time, we can consider the lower band of this bandwidth, which is introduced here, because there is no oscillation in the response of the voltage. So we are sure that as soon as the voltage reaches to this lower bandwidth, it will stay inside the bandwidth, and that will be the response time of the voltage controller. So by setting the second cursor, now just look at the delta y. We want to reach to the value that we obtained as a lower band of the bandwidth. What was that? So 573. We know that the initial value is 1 and this is additional, so we can say that delta t is around 2.2 seconds. So that's how we can obtain a rise time and also response time of the voltage controller. Apart from measuring this response time and rise time, it is also good to play with the features that MATLAB provides. For example, here in this case, we could see the usage of this cursor measurement for measuring the rise time and response time in a very accurate way. Also, I forgot to show you the Q response of the wind turbine when we introduce a step in the voltage. It should look like something like this. It will be a good practice for you to try to understand why reactive power is behaving, is showing this response when we want to have a step voltage from 1 to 1.05 at offshore point of connection. That will be a good, I would say, a good exercise for understanding the overall behavior of the system, and I will leave it to you. This is the end of module 3, and thank you.